You step into the water. It is warm, 28 degrees Celsius, a perfect Caribbean reef temperature. The visibility is extraordinary. You can see the bottom 15 meters down, covered in pink and orange coral colonies that catch the filtered sunlight in shafts. Schools of small silver fish dart through the columns of light. A sea turtle paddles past your shoulder, slow and unhurried. It is, you think, one of the most beautiful dives of your life. But it is not a Caribbean reef. The corals are wrong. They are stromatoporoids, an extinct group of sponge-like reef builders that has not existed for 350 million years. The fish are wrong. They have armored heads and strange jaws lined with bony plates instead of teeth. The sea turtle is not a sea turtle. It is something older, something scallier, with claws on its flippers and a face that does not quite work the way you expect a face to work. You are not where you think you are. You are in the late Devonian 370 million years ago. And in approximately 90 seconds, the largest predator you will ever meet is going to come around that reef and kill you in a way no human has ever been killed before. You do not know this yet. You are still admiring the coral. Your regulator is functioning. Your wetsuit is keeping you comfortable. Your body, for the moment, is alive. The water around you is reasonably oxygenated. The temperature is fine. The chemistry is, in this particular window of geological time, close enough to modern seawater that you have not yet noticed any difference. This is your first 30 seconds in the prehistoric ocean. It feels survivable. It feels almost familiar. Then the shadow arrives. It comes from your left, around the bend of the reef, and it is bigger than anything you have ever seen alive. 6 meters of armored fish, weighing perhaps 3.5 tons. Its head is encased in interlocking plates of bone. Not scales, not skin, plates, the way a medieval knight's armor is plated. Its body trails behind that armored head, more flexible, less protected, but moving with surprising speed. The eyes are small and dark and set forward in the bony mask, and they are looking at you. You see the jaws last. They are the worst part. There are no teeth. Where teeth should be, the bones of the upper and lower jaw have sharpened themselves into blade-like edges. When the mouth closes, those bony blades meet and slice. The bite force has been estimated at 5,000 pounds per square inch at the cutting edge. The mouth opens in 50 milliseconds, faster than your reflexes can process. When it opens, water rushes in, and anything in front of those jaws is pulled forward by the suction. This is Dunkleistus turrelli, the apex predator of the Devonian seas. The reason that period is sometimes called the age of fish. You have time for one thought. 1. The signal from your eyes to your brain takes about 100 milliseconds. The signal from your brain to your muscles takes about another 100. The Dunkleistus opens and closes its jaws in less time than that. By the time your body begins the process of trying to flee, the strike is already complete. You feel nothing. There is no time for nerve signals to reach your brain before the catastrophic injury ends consciousness. The water around you turns red. The Dunkleistus circles once, takes a second piece, and then swims away. The smaller fish emerge to feed on what is left. That is one prehistoric ocean. That is one death. Total elapsed time from entering the water to dying. Approximately 2 minutes. But here is the thing about that scene. The Devonian is not the worst prehistoric ocean. It is not even close to the worst. There are oceans in the deep history of this planet that would have killed you faster, more brutally, and without any predator involved at all. There are oceans that would have boiled you. There are oceans that would have suffocated you within the first breath. There are oceans that would have poisoned you with the water itself, where the air above the water would have killed you if the water somehow did not. There is no prehistoric ocean, none, in the entire 4.5 billion year history of this planet, in which a modern human could survive. The Devonian is, by some measures, one of the more survivable options. Tonight we are going to learn why. So before we begin, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here. And let me know in the comments which prehistoric ocean you would have most wanted to visit. knowing what you now know about your chances? There is something interesting about that question. The answer you give yourself reveals something about how you think about danger, time, and the strange privilege of being alive in this particular geological moment. There is another story that gets told too, and it is also wrong. This one says that prehistoric oceans were just colder or just warmer or just had different animals, but that an unprotected human could probably survive in most of them for at least a little while. After all, water is water. We are mostly water. How bad could it really be? Could be very bad. It would be very bad. The reason most people underestimate the lethality of prehistoric oceans is that we tend to imagine ocean as a single category, with predictable physical properties, varying only in details. But the ocean is not a single thing. The ocean is whatever the planet happens to have at the moment. And the planet has had many different oceans, and most of them were lethal. So let us begin. Let us go all the way back. Let us start at the very beginning with the very first ocean, and let us see what it was like. Picture the Earth 4.5 billion years ago. The planet has just formed from the accretion of smaller bodies in the early solar system. The surface is still partially molten in places. Volcanic activity is constant. Asteroid impacts are frequent. The late heavy bombardment, a period of intense impact activity, will continue for hundreds of millions of years. The atmosphere is thick with carbon dioxide, water vapor, and various sulfur compounds belched out by volcanoes. There is no free oxygen anywhere on the planet. None at all. The moon hangs in the sky, but it is much closer than the moon you know. Perhaps a quarter of its current distance. It looks enormous, dominating the night when the night can be seen at all through the perpetual cloud cover. The day is short, perhaps only 6 hours long, because the impact that formed the moon set the Earth spinning rapidly and the planet has not yet had time to slow down. The sun is dimmer than the modern sun, younger stars produce less light, but the surface temperature of the Earth is still hot, kept that way by the dense greenhouse atmosphere and the residual heat from formation. If you somehow stood on the surface of the Hadean Earth, the experience would be like standing on no other planet you can imagine. The sky is not blue. It is reddish-orange, tinged with the dust and chemistry of a world still cooling from its formation. The horizon flickers with volcanic activity. Asteroids streak across the upper atmosphere on a regular basis, some of them small and harmless, some of them large enough to glow as fireballs even before they strike. The ground beneath your feet trembles with frequent earthquakes. Volcanic ash drifts down in patches. The whole world is, in a real sense, still under construction. Around 4.5 billion years ago, perhaps slightly earlier, the first oceans appeared. They formed when the Earth cooled enough for atmospheric water vapor to condense into liquid. But these were not oceans you would recognize. The water was extremely hot, initially perhaps 200 degrees Celsius or more, kept liquid only by the enormous atmospheric pressure of the early Earth. The pH was acidic, between 4 and 6, comparable to vinegar. The salinity was perhaps twice that of the modern ocean. There was no dissolved oxygen. There was no life. Now imagine you step into this ocean. You have your time machine. You have your wetsuit and your regulator and a tank of modern compressed air to breathe. You step into the water. You die. Almost instantly. The temperature is 200 degrees Celsius. 100 degrees above the boiling point of fresh water at sea level pressure, kept liquid only by the crushing atmospheric weight above it. Your skin, on contact, suffers third-degree burns across every exposed surface. The wetsuit melts where it touches the water. Your body's protein structures begin to denature within milliseconds. Your eyes, behind your mask, are exposed to thermal radiation from the water that is sufficient to boil the vitreous humor inside the eyeball. Within perhaps 10 seconds, your nervous system has shut down. Within 30 seconds, your tissues have begun to cook in the conventional sense. Proteins coagulating, cells rupturing, the soft architecture of your body coming apart. This is the Hadean Ocean. 4.5 billion years ago. Total elapsed time from entering the water to dying. Less than a minute. There is no predator. There is no competition. There is just water that is hot enough to cook a human being. And even if you somehow survived the temperature, if you were wearing some impossible heat-resistant suit that protected your body from the boiling ocean, you would still face the air. The Hadean atmosphere had no oxygen. Your tank of compressed modern air would last for whatever time the tank held, perhaps 30 minutes for a typical scuba setup. Once the tank ran out, you would have nothing to breathe. The atmosphere overhead would not be air in any sense your body could use. It would be carbon dioxide, water vapor, sulfur compounds, and traces of other gases produced by volcanic and impact processes. Within 2 minutes of running out of tank air, you would lose consciousness. Within 10 minutes, you would be dead. But here is the thing. Even surviving the temperature and breathing your tank, the bombardment would probably get you anyway. The late heavy bombardment was not a constant rain of small meteors. It included occasional very large impactors, the kind that boiled off entire ocean basins and filled the atmosphere with rock vapor. To stand on the early Earth, even briefly, was to stand on a world subject to catastrophic disruption at any moment. A statistical analysis of impact rates during the Hadean suggests that the chances of a major impact occurring within any given year were not negligible. Within any given decade, they approached certainty for impacts large enough to reset surface conditions across substantial regions. The Hadean was not just lethal because of its chemistry. It was also lethal because of the cosmic violence that was an ongoing feature of its environment. This is the first lesson of our journey. The earliest oceans on Earth were not bodies of water as you understand them. They were chemical reactors. They were environments in which the conditions for life as we know it did not yet exist. They were not just dangerous. They were physically incompatible with you at the most basic level. The Hadean lasted for several 100 million years before the planet finally cooled enough to be merely lethal rather than instantly lethal. Let us move forward. Step into the Archean Ocean 3.5 billion years ago. The planet has cooled. The asteroid impacts are less frequent. The temperature of the surface water is no longer scalding, perhaps 50 or 60 degrees Celsius at the surface, hotter than a hot bath but not boiling. The pH has risen slightly to perhaps 6. The atmosphere is still oxygen-free, but it is now also rich in methane, produced by microbial life that has begun to evolve in the warm seas. Yes, life. By the Archean, the first organisms have appeared. They are simple, single-celled, microbial. There are bacteria. There are archaea, a separate domain of single-celled life that includes some of the most extreme condition specialists on the modern Earth. There are no plants, no animals, no fungi. Nothing complex. Just microbes, but microbes in enormous numbers, building structures called stromatolites, layered mats of bacterial growth that grow upward from the seafloor over centuries, forming domes and columns that can reach several meters tall. Picture an Archean shallow sea. The water has a green tint from the dissolved iron and from the cyanobacteria that bloom near the surface. Where iron precipitates out, the water turns rust-colored. Where stromatolites grow, the seafloor is covered in dome structures that look almost like alien architecture. The sky overhead is hazy. The methane in the atmosphere reacts with sunlight to produce an orange-tinted smog that hangs over the planet, giving the daylight a strange ochre quality. The sun, dimmer than the modern sun, struggles through this haze. There are no clouds in the modern sense, but there are layers of atmospheric chemistry that make the sky look nothing like the blue you know. You step into this water. You die again, differently this time. The temperature is uncomfortable but not immediately lethal. 50 or 60 degrees is hot, hot enough to cause heat exhaustion within an hour, hot enough to cause organ damage if you stayed in for several hours, but not hot enough to kill you in the first few minutes. The acidity is mild. The microbes in the water are not adapted to invade human tissues, so they will not infect you immediately. You could, in principle, swim in the Archean Ocean for a little while. The problem is the air. The Archean atmosphere had essentially no oxygen. Not low oxygen. Not reduced oxygen. None. Once your modern compressed tank ran out, you would be breathing methane and carbon dioxide and nitrogen with no oxygen at all. Your blood would carry no oxygen to your tissues. Your brain, which uses about 20% of your body's oxygen consumption despite being only 2% of your body weight, would shut down quickly. Within 2 minutes of breathing oxygen-free air, you would lose consciousness. Within 6 minutes, you would suffer permanent brain damage. Within 10 minutes, you would be dead. This is the Archean Ocean. Total elapsed time from running out of tank air to dying, about 10 minutes. The water itself does not kill you. The atmosphere kills you by simply failing to contain the molecule your cells require. Move forward another billion years. The Proterozoic. Specifically, the Middle Proterozoic around 1.5 billion years ago. By now, atmospheric oxygen has begun to accumulate. Slowly. There is more oxygen than in the Archean, but not nearly enough. And the deep ocean is doing something strange. This is the era of what some geochemists call the Canfield Ocean. Donald Canfield's hypothesis. The shallow surface waters of the Middle Proterozoic Ocean were oxygenated, at least in places. But the deep waters were not. The deep waters were anoxic, oxygen-free, and in this anoxic environment, sulfate-reducing bacteria thrived. These bacteria consume sulfate and produce hydrogen sulfide as a metabolic byproduct. Over hundreds of millions of years of operation, they built up substantial concentrations of dissolved hydrogen sulfide in the deep ocean. You step into a Proterozoic shallow sea. The surface water tolerates you at first. The atmosphere is breathable barely, perhaps a tenth of modern oxygen levels, equivalent to standing on the summit of a high mountain peak. You can breathe, but only just. Your body is hypoxic. Your decision-making is impaired. Sustained physical exertion is impossible. You feel constantly short of breath, slightly dizzy, the way you would feel at extreme altitude. But you do not die immediately. You can survive in the surface water for a little while. You decide to dive, to look at the strange microbial communities below, to see what the Proterozoic Ocean looks like at depth. You descend. 20 meters. The water is dim. The microbial communities thin out. The dissolved oxygen content drops with depth. At 30 meters, the water tastes wrong. There is something acrid in it, something that makes your skin tingle through the wetsuit. At 40 meters, you can smell hydrogen sulfide through your regulator, the unmistakable rotten egg odor leaking through the seal. You should turn back, but you have already breathed in too much of it. Hydrogen sulfide is acutely toxic. At concentrations of a few hundred parts per million, it disables the olfactory nerve, so you stop being able to smell it. At concentrations of 1,000 parts per million, it paralyzes the respiratory system. At concentrations above 2,000 parts per million, it kills almost instantly by binding to cellular respiration enzymes and shutting down energy production at the molecular level. The deep waters of the Canfield Ocean had concentrations that may have reached or exceeded these lethal thresholds in some basins. You die. Not from drowning, not from a predator, not from temperature. From a poison gas dissolved in the ocean itself. The Proterozoic Ocean, in its deep waters, would have killed you with chemistry. Total elapsed time. A few minutes. We have so far visited 3 prehistoric oceans, and we have died in 3 different ways. Burning, suffocation, gas poisoning. None of these involved any predator. None involved any animal larger than a bacterium. The water itself or the air above it killed you in each case. We have not yet reached the era of complex animals. The Earth has had oceans for approximately 4 billion years at this point in our journey, and during 3/4 of that time, the most lethal thing about those oceans was the chemistry. Let us continue. Move forward to the late Proterozoic. The Cryogenian and Ediacaran periods, roughly 700 million to 540 million years ago. The Earth has gone through some dramatic climate shifts during this interval, including possibly 2 or 3 snowball Earth episodes when the entire planet, oceans included, was covered in or filled with ice. The chemistry of the ocean has begun to change. Atmospheric oxygen has begun rising again. The first complex multicellular animals are starting to appear, soft-bodied creatures with body plans that often do not match anything alive today. You step into an Ediacaran ocean, perhaps 570 million years ago. The water is cool, the planet is recovering from its frozen episodes, and the atmosphere has more oxygen than the Proterozoic, perhaps 30 to 50% of modern levels. You can breathe surface air with effort. You can see strange soft-bodied creatures sliding across the seafloor, frond-like organisms attached by holdfasts and waving in slow currents, quilted disc-shaped animals that have no obvious head or tail. Some of these creatures are large, more than a meter across. None of them are predators. The Ediacaran was a relatively peaceful era, ecologically speaking, because the chemistry of the ocean still could not support the metabolic intensity of true predator-prey ecosystems. The animals existed, but they fed on microbial mats and dissolved organic matter, not on each other. You could swim through this ocean without being attacked. You would still die. Slower this time. The atmosphere is still hypoxic by your standards. The microbial environment, while not actively predatory, contains lineages your immune system has never encountered. Wounds infect rapidly. Mucous membranes, your eyes, your mouth, your respiratory tract, develop inflammatory responses to unfamiliar pathogens. Within hours of exposure, you would feel sick. Within a day, you would be very sick. Within a week, even if nothing larger than a microbe attacked you, you would be dead from infections that no modern medicine has been designed to treat. This is the slow killer. The Ediacaran Ocean would not strike you down in seconds, like the Hadean. It would simply refuse to accommodate your immune system, and your body would gradually fail. But the next ocean you visit is the Cambrian, and the Cambrian is when prehistoric oceans start to feature predators that can actively kill you. Now there is a story that gets told about the Cambrian. It says the Cambrian was a peaceful, gentle ocean filled with strange but harmless invertebrates. Trilobites scuttling along the seafloor. Soft-bodied creatures drifting in shallow waters. The whole period imagined as a kind of marine kindergarten, full of curious little animals that are not yet aggressive enough to be threatening. Many popular accounts of the Cambrian explosion present it this way, as the gentle dawn of complex life before the real predators showed up. The story is wrong. The Cambrian had predators. Real predators. Predators that hunted and killed and ate other animals. The arms race between hunters and hunted began as soon as complex life began. Within a few million years of the first multicellular animals appearing, there were already creatures specialized to eat them. The Cambrian explosion was not just an explosion of animal diversity. It was an explosion of predation, with all the violence and competition and ecological complexity that predator-prey relationships always bring. Picture a Cambrian shallow sea, around 520 million years ago. The water is warm, warmer than modern tropical seas, perhaps 35 degrees at the surface. The seafloor is covered in trilobites, those iconic Cambrian arthropods, in dozens of species, most of them the size of your hand. Strange spiked creatures crawl across the bottom, early relatives of arthropods with body plans that look almost cartoonish in their unfamiliarity. Tube-dwelling worms extend feathery feeding apparatuses into the water column. The Burgess Shale, the famous Canadian fossil site that gave us our first clear window into Cambrian life, preserves these communities in extraordinary detail. We know what they looked like. We know roughly how they lived. We know that the Cambrian explosion produced an extraordinary diversification of body plans, with most modern animal phyla appearing in a relatively short geological window. The light reaching you is different from modern ocean light in subtle ways. The Cambrian atmosphere had higher concentrations of carbon dioxide and methane than today, and the resulting greenhouse haze gave the sky a pale yellowish tint that filtered down through the water. The sunlight is dimmer in absolute terms than modern sunlight. The early sun was still gradually brightening, but the increased greenhouse effect kept the surface warm. The combination produces a slightly murky, golden-tinted light underwater, different in character from the clear blue-white shafts you would see in a modern tropical reef. The water also smells different. Or rather, it would smell different if you could smell anything through your scuba mask. The chemical composition of dissolved gases is not quite modern. There is more dissolved carbon dioxide. There is less dissolved oxygen. There are trace gases produced by microbial metabolism that you would not encounter in a modern ocean. If your skin made contact with the water, through gaps in your wetsuit or simply through prolonged exposure, your body would notice the difference. Mild irritation, slight itching, the feeling of being in water that is almost right but not quite right. The atmospheric oxygen of the Cambrian was about half of modern levels. Breathing the surface air would feel like breathing the air at 3,000 meters of altitude. Possible, uncomfortable, sustained exertion would be exhausting. Your body would be running constantly in mild hypoxia. You float in the warm Cambrian water. You watch the trilobites. You marvel at the strangeness of the life around you. And then you see something coming. It is about a meter long, flattened body. 2 large eye stalks projecting from the head, each containing thousands of compound facets. A pair of grasping appendages at the front, segmented, each tipped with hard cuticular spines arranged in rows. Behind the body, lateral flap-like fins undulate in waves that travel along the length of the animal, producing smooth forward motion. The mouth, which you cannot see clearly until the creature is close, is a circular structure on the underside of the head, lined with overlapping plates that close together like the iris of a camera. This is Anomalocaris, the largest predator of the Cambrian, the apex of the food chain in an ocean where the food chain was still being constructed. Anomalocaris is not particularly impressive by the standards of later prehistoric predators. It is smaller than a modern dolphin. It does not have impressive teeth. This body plan is alien, but it is not, in any modern sense, terrifying. Except for one thing. Its compound eyes contain more individual lenses than any modern arthropod's eyes, possibly more than 16,000 facets each. It can see you with extraordinary acuity. It is assessing you. The grasping appendages, which look almost like jointed pincers, are the most sophisticated grasping apparatus any animal has yet evolved on Earth. They are designed to hold soft-bodied prey in place while the disc-shaped mouth processes it. And you are very soft-bodied. The Anomalocaris approaches with what looks like leisurely curiosity. The compound eyes track your every movement. The grasping appendages extend, slowly, as if to test whether you are food. They make contact with your wetsuit. The cuticular spines press against the rubber. The animal evaluates the texture, the resistance, the size. You try to swim away. The hypoxia of the Cambrian atmosphere has already exhausted your muscles. You cannot swim fast. The grasping appendages close. The Anomalocaris pulls you toward the disc mouth. The plates contract. The bite is not powerful in absolute terms. Anomalocaris does not have the bite force of a Devonian Dunkleistus or a Jurassic pliosaur. But the bite does not need to be powerful. It needs only to puncture. Once the disc mouth has taken its first piece of you, blood pours into the surrounding water. The smaller predators of the Cambrian, and there are many of them, swimming arthropods, primitive fish-like creatures, smaller predatory worms, converge on the source of the blood. Your body is consumed in pieces by many mouths at once. Total elapsed time from Anomalocaris first sighting you to your death. Maybe 10 minutes. You did not die in seconds like in the Devonian. You died slowly, attacked first by an apex predator that was, by modern standards, not very fast or very deadly, but that was still more than enough to kill you. The Cambrian killed you with its top predator. And the top predator of the Cambrian, the most fearsome thing in the entire Cambrian Ocean, was a meter-long arthropod that would not even register as a threat to a modern shark. This is what we are dealing with. Even in eras when the apex predator was modest, it was still an apex predator, and you were still a soft-bodied creature unfamiliar with its hunting techniques. The Cambrian Ocean had no place for you, and within minutes of your arrival it would dispose of you. But here is the part of the Cambrian story that almost no one tells. Anomalocaris was not the only thing in the water that could have killed you. The Cambrian was full of smaller predators that, individually, would have been minor inconveniences, but collectively were a serious problem. There were predatory priapulid worms, lying in burrows in the sediment, ambushing prey that came too close. There were nectaspid arthropods that may have been active hunters of small fish. There were primitive vertebrates, the earliest fish-like creatures, that had already begun the predatory career that would eventually produce sharks and Dunkleistus and modern barracudas. The Cambrian was an ocean of small predators competing fiercely for the abundant new prey species. Even if Anomalocaris had not killed you, the cumulative effect of being repeatedly investigated and attacked by smaller hunters would have been lethal within hours. The Cambrian was not gentle. The Cambrian was the beginning of the predatory ocean we have lived with ever since. Move forward. The Ordovician. 450 million years ago, the shallow seas of the Ordovician were richer than the Cambrian, with the first true reefs, the first diverse cephalopod communities, the first complex marine ecosystems in something like modern form. And the apex predators of the Ordovician were a lineage that has since gone extinct entirely. The straight-shelled nautiloids. Picture a Camarasaurus, the largest predatory cephalopod of the Ordovician, possibly of all geological time. The shell is a long pale tube, perfectly straight, 6 to 10 meters long depending on the species. The living animal occupies the open end of the shell, with tentacles extending outward in a fan, each tentacle as thick as a human arm. Behind the tentacles is a large beak, made of chitin, capable of crushing the shells of trilobites and the bones of small fish. The shell is filled with chambered air spaces that the animal can flood or empty to control its buoyancy, allowing it to rise and sink in the water column with precision. You enter an Ordovician sea. You see the Camarasaurus coming, slowly, drifting through the water like a giant pale telescope. The tentacles fan out, looking for prey. You think you have time to retreat. You are wrong. The tentacles, despite their apparent slowness when they are simply extended, can lash out with surprising speed when they make contact with something edible. They are not muscular in the way a vertebrate limb is muscular. They use a hydrostatic system of pressurized fluid to extend and retract. The mechanism is fast. The tentacles wrap around your torso. You feel them tighten. The suckers, modern cephalopods have suckers, and Camarasaurus almost certainly had them too, adhere to your wetsuit and to any exposed skin. You try to break free. The tentacles are too strong. You are pulled toward the shell opening, toward the beak. The beak crushes downward through the wetsuit, through the muscle and bone of your shoulder, through your collarbone. Camarasaurus feeds on you while you are still alive. The blood spreads through the water in the same pattern it spread in the Cambrian and the Devonian. Other smaller predators converge. This is the Ordovician death. Total elapsed time, a few minutes. The Ordovician also ended with one of the most severe mass extinctions in Earth's history. About 443 million years ago, an extinction event killed approximately 85% of marine species. The cause was probably a brief but severe glaciation event, combined with sea level drop and oceanographic changes. If you visited the latest Ordovician during the extinction itself, you would find an ocean undergoing collapse. Cold, anoxic in many regions, most of its species dying. The chemistry would have been hostile in addition to the predators. The Silurian, which followed the Ordovician extinction, was a recovery phase. New species evolved to fill the empty niches. Reefs rebuilt, and the Eurypterids, sea scorpions, reached their maximum diversity. Some species were small and harmless. Some were enormous. Imagine a Silurian sea 425 million years ago. The water is shallow, perhaps 15 meters deep. The seafloor below is covered in primitive plants and small creatures. The water is full of small fish and arthropods. And then you see it. Pterygotus, 2.5 meters long. Body segmented like a giant lobster. 2 enormous claws projecting from the front of its head. Each claw lined with serrated teeth on the inner surface. Eyes mounted on the upper surface of the head, watching you. Pterygotus is not a fast pursuit predator. It is an ambush hunter. It has been waiting on the seafloor, partially buried in sediment, until something comes within reach of those claws. You are within reach. The strike is fast. Pterygotus extends its body upward off the seafloor and lunges. The claws snap closed around your leg. The serrated edges of the claws cut through the wetsuit and into the muscle. You are pulled toward the body, toward the mouth on the underside of the head. The mouth, like the mouth of all eurypterids, is small relative to the body, but it does not need to be large. The arthropod feeds slowly in pieces while you bleed out. The Silurian has killed you with its largest sea scorpion. Total elapsed time: 10 or 20 minutes, depending on the rate of blood loss. Slower than the Devonian, faster than the Cambrian. Move forward now to the Devonian, which is where we started this journey. We have already seen what the Devonian does to you. Dunkleistus, 2 seconds of warning. Sliced in half. We will not relive that scene. But we should note that the Devonian was not just the era of one giant placoderm. It was also the era of multiple anoxic crises. The late Devonian extinction was actually a series of pulses spread over perhaps 15 million years, and during each pulse the ocean lost oxygen across vast areas. If you visited the Devonian during one of these anoxic events, you would face not only the placoderms but the chemistry itself. The deep waters would be lethal even without predators in them. There is something worth pausing on here, because the Devonian, more than any other prehistoric ocean we have visited, illustrates a particular kind of danger that the modern ocean does not present. The Devonian was an ocean of multiple-tier predators, all of which could have killed you. There was Dunkleistus, the apex armored fish. There was Hyneria, a 4-meter lobe-finned predator that hunted in coastal waters and rivers. There were primitive sharks, smaller than modern sharks but still dangerous, in their own right, beginning to occupy the niches their descendants would later dominate. There were eurypterids, sea scorpions of the largest sizes, still present from the Silurian. There were primitive squid-like cephalopods, some of them sizable predators in their own right. In other words, even if you somehow escaped Dunkleistus, you would not have escaped the Devonian. There were too many other predators. The ecosystem was densely populated with hunters of various sizes, all of them perfectly capable of killing a soft-bodied human swimmer. And the late Devonian extinction is itself worth understanding, because it tells us something about how oceans fail. The cause is debated, but several factors seem to have contributed. The first land plants were spreading and getting larger, drawing nutrients out of soils and channeling them into rivers. Those nutrients flowed into the oceans, fueling massive plankton blooms. The plankton died, sank, and decomposed, consuming oxygen as they did so. The deep ocean lost oxygen. Anoxia spread. Marine animals that depended on dissolved oxygen began to die. Multiple pulses of this kind of biogeochemical disruption, spread over 15 million years, killed about 75% of marine species. The placoderms, including Dunkleistus, were among the major casualties. The entire group went extinct by the end of the Devonian, leaving no descendants. This is worth noting, because it means that the most fearsome marine apex predator of that era simply could not survive its own ocean's environmental collapse. The bite force did not matter. The armor did not matter. The hunting prowess did not matter. When the chemistry shifted, even the best predator died. The Carboniferous, which followed the Devonian, is a strange interlude. Atmospheric oxygen reached its highest levels in Earth's history during the Carboniferous, perhaps 35% compared to today's 21%. This had bizarre effects. Insects on land grew to enormous sizes. Dragonflies with wingspans of 70 centimeters. Millipedes 2 meters long. The ocean was also affected, with marine life supporting higher metabolic rates than in earlier or later periods. If you stepped into a Carboniferous sea, the higher oxygen would actually feel pleasant. You would be slightly more energetic than usual, your blood saturating more efficiently, your muscles feeling slightly fresher than they do in modern conditions. For a moment, this might seem like the most habitable prehistoric ocean we have visited. It is not. The high oxygen environment also supported larger and more active predators. And the Carboniferous had its own peculiar predators. One of them was Helicoprion, a shark-like fish whose lower jaw contained a spiraling whorl of teeth. Not teeth in the normal arrangement, but a tightly coiled structure of dozens of teeth arranged in a single spiral row. The function of this tooth whorl is still debated by paleontologists. Some researchers believe it was used to slice through soft-bodied prey. Others believe it functioned as a kind of saw. Whatever its precise function, the Helicoprion tooth whorl is one of the strangest dental structures ever evolved by any vertebrate. You enter a Carboniferous sea. You see something coming. It is shark-shaped, 4 to 7 meters long depending on the species. As it gets closer, you see the lower jaw, the whorl, the spiral of teeth that does not look like any predator you have ever imagined. Helicoprion attacks. Whatever the precise mechanism, the result is that the spiral of teeth slices through your soft tissue with the grain of the rotation. You die of catastrophic blood loss within minutes. The Carboniferous and the early Permian also had something else. Strange ammonoid cephalopods that grew to substantial sizes. Predatory sharks of various lineages, some of them reaching 3 or 4 meters. Eugeniodonts, the family that included Helicoprion, were diverse and successful, with many species occupying different niches in different habitats. And the precursors of the marine reptiles, although those would not reach their full development until the Mesozoic. But the Permian, the end of the Permian, 252 million years ago. This is the worst of all the prehistoric ocean death scenarios. Not because of predators, because of the chemistry of the ocean itself. You should pay particular attention to this one, because the end Permian is the closest analog we have, in deep geological time, to what happens when a planet's entire ocean becomes hostile to complex life. It is the worst-case scenario. It is the kind of marine environmental collapse that geologists hope, with some anxiety, will not occur again anytime soon. The Permian-Triassic extinction killed approximately 96% of marine species. The cause was a chain of events triggered by the Siberian traps, enormous volcanic eruptions in what is now Siberia that, over a period of perhaps 1 million years, released vast quantities of greenhouse gases and toxic compounds into the atmosphere and oceans. The total volume of erupted material was approximately 7 million cubic kilometers, enough to cover the entire surface of the Earth in a layer of basalt more than 1 centimeter thick. The eruptions drove global warming. They drove ocean acidification. They drove anoxia across vast areas of the deep sea. And in the anoxic regions, sulfate-reducing bacteria proliferated, producing hydrogen sulfide that accumulated in the deep waters and, in some basins, may have risen all the way to the surface and into the atmosphere. To put the Siberian traps in perspective, consider this. Modern volcanic eruptions, the kind that get global news coverage, release millions of cubic meters of material. The eruption of Mount St. Helens in 1980 released about a cubic kilometer of material. Pinatubo in 1991 released about 10 cubic kilometers. The Siberian traps, over their full duration, released 7 million cubic kilometers. The scale is so different that direct comparison breaks down. The Siberian traps were not just a large eruption. They were a sustained, planet-altering volcanic event that lasted longer than the entire history of the human genus. The atmospheric and oceanic consequences played out over hundreds of thousands of years, but the cumulative effect on the marine environment was unprecedented in the entire history of complex life. The ocean became hot. Surface temperatures in the tropics may have reached 40 degrees Celsius, too hot for most marine life to function. Coral reefs collapsed. Plankton communities collapsed. The fish populations that depended on plankton collapsed. The predators that depended on fish collapsed. The entire food web was unraveling from the bottom up. If you visited the late Permian Ocean, just before the extinction, you would find a world in environmental decline. The water was warm and growing warmer. The acidification was beginning to dissolve carbonate shells. The deep ocean was losing oxygen. The atmosphere overhead was uncomfortable to breathe, enriched with volcanic carbon dioxide and sulfur compounds. If you visited during the actual extinction event, conditions would have been catastrophic. Hot, acidic, oxygen depleted, hydrogen sulfide bubbling up from the deep. The combination of these factors created an ocean that almost no complex animal could tolerate. Trilobites, after surviving for more than 200 million years, went extinct entirely. Most reef-building organisms died. Most fish species died. And if you visited the early Triassic just after the extinction, you would find an ocean that was still broken. The recovery from the Permian extinction took millions of years. For the first several million years after the boundary, the ocean was simply not a functional habitable environment. Some researchers have called this the dead ocean interval. The marine ecosystems we recognize did not exist. Microbial mats, the old Archean and Proterozoic ecosystem type, returned to dominate the shallow seafloors that should have been covered in animal communities. The ocean had been reset. You enter a Triassic ocean 5 million years after the Permian extinction. The water is hot, surface temperatures still 40 degrees in the tropics. The deep waters still anoxic across vast regions, still containing dissolved hydrogen sulfide that would kill you on contact. The fauna is depauperate, dominated by a few opportunistic species. The food web is broken. There is almost no apex predator, because almost no large animals have evolved yet. You die not from a predator but from the basic chemistry of the ocean, either the heat, or the acidity, or the hydrogen sulfide drifting up from below, or the mild hypoxia of the disrupted atmosphere, or some combination of all of these acting together. The Permian-Triassic Ocean would kill you with its environment, the way the Hadean killed you with its temperature. This is the worst prehistoric ocean, the one that would refuse to host any complex life form, our own included. But here is what is interesting about the end Permian. It teaches us something the other prehistoric oceans cannot teach. The other oceans we have visited tonight were lethal because they were chemically different from our ocean from the start. The Hadean was lethal because it had never been habitable. The Archean was lethal because it had not yet developed oxygen. The Cambrian was lethal because it was full of unfamiliar predators. These were oceans that had simply not yet become the modern ocean. The end Permian was different. It had been a normal, complex marine ecosystem for hundreds of millions of years. Fish, cephalopods, reef-building corals, diverse plankton, all of it. Then, over a few 100,000 years, it collapsed. The chemistry shifted. The ecosystems unraveled. The ocean that had been functional became dysfunctional. And it took millions of years to recover. The end Permian shows that oceans can become uninhabitable. It is not a hypothetical. It happened. The same chemistry that made the early Triassic Ocean lethal, heat, acidification, hypoxia, sulfide, could in principle happen again, if conditions on the planet pushed in that direction. We hope they will not, but the Permian shows us that they can. Now move forward. The Triassic recovers, slowly. By the late Triassic, 220 million years ago, marine ecosystems are functional again. New species have evolved to fill the empty niches. The first marine reptiles, ichthyosaurs, the early ancestors of the great Mesozoic sea dragons, have appeared. The ocean is no longer an environmental wasteland. It is, however, full of large predators. The Jurassic, which followed the Triassic, is the heyday of the marine reptiles. We have discussed this period extensively in another documentary. The relevant points for our purposes here are these. The Jurassic Ocean was full of large predators. Pliosaurs of enormous size, 12 to 15 meters long, with bite forces that exceeded any modern predator. Ichthyosaurs of various species, dolphin-shaped reptiles with eyes the size of dinner plates, hunting in the open ocean. Plesiosaurs threading their long necks through coral reefs. Marine crocodilomorphs patrolling the lagoons. Predatory fish, including the largest bony fish ever to have existed, leadsichthys, although that one was a filter feeder rather than a predator. There is something specifically worth understanding about the Jurassic predators. Their bite forces, calculated by paleontologists studying the fossil skulls and applying biomechanical analysis, are higher than any modern predator's bite forces. The estimated bite force of Pliosaurus funke, the largest pliosaur, is approximately 33,000 pounds per square inch. For comparison, a modern saltwater crocodile, the strongest biting living animal, manages about 3,700 pounds per square inch. A great white shark around 4,000. The pliosaur could bite with 8 to 10 times the force. There is no animal currently alive that comes close. You enter a Jurassic Ocean. You float in the warm tropical water. You see, far below you, a shape rising. It is large, very large. As it gets closer, you can see the 4 enormous flippers, the short thick neck, the massive head. The skull is 2 meters long. The eyes are the size of soccer balls. The teeth are the size of bananas. This is Pliosaurus funke, the largest known pliosaur, 14 meters long, weighing 45 tons, with a bite force estimated at 33,000 pounds per square inch, stronger than a Tyrannosaurus rex. The Pliosaurus comes up underneath you. You do not have time to react. The bite catches you across the torso. The interlocking teeth puncture and crush. You are dead before you register the impact. The pliosaur swallows you in 2 pieces and continues swimming, looking for other prey. The Jurassic Ocean has killed you with its apex marine reptile. Total elapsed time: less than a minute. The Cretaceous, which followed the Jurassic, was the final phase of the Mesozoic. The Cretaceous saw the rise of new marine reptile groups. The mosasaurs in particular, which were giant marine lizards related to modern monitor lizards. Some mosasaurs reached lengths of 15 meters or more. They had powerful jaws lined with conical teeth designed for grasping and crushing prey. They had double-hinged jaws that allowed them to swallow large prey whole. They were apex predators of the late Cretaceous seas, occupying the niches that pliosaurs had held during the Jurassic. The mosasaurs are particularly worth describing because they evolved late in the Mesozoic and quickly became the dominant marine predators of the final 25 million years of the dinosaur era. Their lineage began in the early late Cretaceous around 100 million years ago, when terrestrial monitor lizards adapted to marine life. Over the next 30 million years, mosasaurs diversified into dozens of species ranging from small coastal hunters less than a meter long to giants like Mosasaurus hoffmanii, which reached 15 to 17 meters and weighed perhaps 15 tons. Picture a Mosasaurus hoffmanii, 17 meters long, 15 tons. Body shaped like a giant monitor lizard but adapted to fully aquatic life. Paddle-like limbs, a long muscular tail with a vertical fluke, a head shaped for fast pursuit and powerful biting. Some mosasaur fossils show stomach contents including other mosasaurs, sharks, and full-size sea turtles. They were not picky. You enter a Cretaceous western interior seaway, the shallow inland sea that covered much of central North America during the late Cretaceous. The water is warm. The visibility is good. You see, in the distance, a long dark shape moving through the water. It is hunting. It has detected you. It is approaching. The mosasaur strikes. The bite catches you. The double-hinged jaws open wide, and you are pulled into the throat. There is no escape from a mosasaur bite, because the jaws are designed to swallow prey whole rather than to chew it. You disappear into the throat of an animal the size of a city bus, alive but unable to breathe, drowning in the digestive cavity of a giant marine lizard while it swims slowly back to deeper water. This is the Cretaceous death. Worse than the Jurassic in some ways because at least the pliosaur killed you quickly. The mosasaur swallows you alive. The Cretaceous oceans also had other threats. Large Cretaceous sharks, including some species reaching 10 meters or more, hunted in the open ocean. Cretoxorina, sometimes called the Ginsu shark for its slicing teeth, reached perhaps 7 meters and was an active predator of marine reptiles and large fish. Squalocorax, the so-called crow shark, was smaller but abundant, and is known for many fossils preserved with bite marks on the bones of its prey. The Cretaceous western interior seaway was full of these predators, including mosasaurs of the largest sizes, plesiosaurs, large fish, and the occasional sea turtle of significant dimensions. Archelon, the largest sea turtle that ever lived, swam in this seaway and reached lengths of more than 4 meters across the shell. If you somehow escaped the mosasaurs and the sharks, you would still face the Cretaceous oceanic anoxic events. Several times during the Cretaceous, particularly around 120 million years ago and 93 million years ago, the global ocean went through periods of widespread oxygen depletion. These events killed substantial fractions of marine fauna and produced black shales rich in organic matter. During these anoxic intervals, the chemistry of the Cretaceous ocean would have been hostile to a modern human visitor as well. The deep waters would have been anoxic across vast areas. Hydrogen sulfide may have accumulated in some basins. The food web would have been disrupted. Move forward. The end of the Cretaceous. 66 million years ago. The asteroid that killed the dinosaurs strikes the Yucatan. The ocean is reset again. Mosasaurs, plesiosaurs, ammonites, all extinct. The Cenozoic begins. The Paleogene Ocean is, in many ways, calmer than the Mesozoic Ocean was. The marine reptiles are gone. The first whales begin to evolve from terrestrial ancestors. Sharks continue to diversify. The chemistry of the ocean is approaching modern values. If you visited the early Paleogene, you might survive longer than in any prehistoric ocean we have visited so far. Maybe hours before something killed you. The major predators were sharks of moderate size, early whales that had not yet reached their later large forms, and various predatory fish. Nothing the size of a pliosaurus or a mosasaurus. But by the Miocene, 23 million years ago to about 5 million years ago, the ocean had developed two new apex predators that put us back in serious danger: Megalodon and Livyatan. We have discussed both of these in detail in other documentaries. Megalodon, the largest predatory shark that ever lived, 18 meters long, weighing perhaps 50 tons, with serrated triangular teeth 18 centimeters long. Livyatan, the macroraptorial sperm whale, 15 meters long, 50 tons, with 36 centimeter conical teeth in both jaws and a bite force estimated at 200,000 newtons. Both species hunted whales. Both would have considered you, if they encountered you, a potential snack. Both lived in the warm coastal waters of the late Miocene Pacific and Atlantic. The Miocene is, in some sense, the last great age of marine apex predators. After Livyatan went extinct around 7 million years ago and Megalodon went extinct around 3.5 million years ago, the oceans entered a phase of reduced apex predator size that has continued to the present day. The largest modern predators, orcas, great whites, are smaller than what the Miocene contained. The current ocean has, by the standards of recent geological time, relatively modest apex predators. You enter a Miocene ocean. You are floating in clear blue water off the coast of what would one day be Peru. You see two shadows. One is enormous and shark-shaped. The other is enormous and whale-shaped. They are approaching from different angles. You are between them. You die. It does not matter which of them gets to you first. The bite force is comparable. The result is the same. The Miocene Ocean has killed you with its two apex predators, simultaneously, in a way that no other prehistoric ocean could quite match for sheer scale. By the Pliocene, 3 million years ago, Megalodon had gone extinct. Livyatan had gone extinct earlier. The great Miocene apex predators were gone. The ocean was approaching its modern configuration. By the Pleistocene, 2.5 million years ago, the modern ocean was essentially in place, with the addition of some species that have since gone extinct due to human activity. We have now visited every prehistoric ocean. We have died in every single one of them by different mechanisms at different speeds for different specific reasons. The cumulative pattern is clear. There is no era of the prehistoric ocean in which a modern human could survive for very long. Some eras would have killed us in seconds, some in minutes, some in hours or days. None would have allowed us to live a normal life. So let us now ask the question that has been hanging over this entire documentary. Why? Why is a modern human so completely incompatible with the deep history of the Earth's oceans? Why are we so fragile, so demanding in our environmental requirements, so easy to kill across so many different geological eras? Let us consider this systematically. Across the prehistoric oceans we have visited tonight, we have died from at least 6 distinct categories of cause. Each one is worth pausing on because each one represents a different way that the modern ocean has been set up to keep us alive, a different gift, in other words, of the present. The first category is atmospheric chemistry. The atmosphere over a prehistoric ocean is not always air in the sense that your body needs. The Hadean had no oxygen at all. The Archean had no oxygen at all. The Proterozoic had only trace oxygen, far too little for sustained human metabolism. The Cambrian had about half of modern oxygen levels. The Carboniferous had too much oxygen, which would actually have been pleasant for short exposures but problematic for long ones. The Permian had air contaminated with volcanic gases and possibly hydrogen sulfide. Even the eras with breathable atmospheres often had subtle differences in trace gas composition that would have caused chronic effects over time. Modern atmospheric oxygen at 21%, in a stable mixture with nitrogen and minor gases, is one specific configuration out of many possible configurations, and our bodies are tuned to that one. The second category is water chemistry. The pH, the salinity, the dissolved gas content, the trace metal composition, the dissolved organic compounds, every one of these has varied across geological time, and every one of them has been outside human tolerance ranges in at least some prehistoric eras. The Hadean was acidic and salty. The Proterozoic deep waters contained lethal hydrogen sulfide. The Permian was hot and acidic. The early Triassic was a chemical wreck. Even the eras whose surface waters were chemically tolerable often had trace components that would have caused gradual physiological problems if you stayed in long enough. The third category is temperature. The Hadean was scalding. Several other intervals had tropical surface temperatures of 40 degrees or higher, too warm for human thermal regulation if you stayed in for hours. The deep oceans of various eras were warmer than modern deep oceans, which would have affected dissolved gas content and microbial communities in ways that compound the chemical and biological challenges. The fourth category is predators. We have seen the predators throughout. Dunkleistus, Anomalocaris, Camarasaurus, Pterygotus, Helicoprion, Pliosaurus, Mosasaurus, Megalodon, Livyatan. Each prehistoric ocean had its apex predators, and most of those apex predators would have killed you if they encountered you. The modern ocean has predators too, but the largest are smaller and less common than in many prehistoric eras, and they are predators that you can largely avoid through reasonable behavior. The fifth category is microbes. This is the silent killer that we have only briefly mentioned, but it deserves emphasis. Every era of marine life had its own microbial communities: bacteria, archaea, viruses, and various other tiny organisms that played essential roles in marine ecosystems. Your immune system, the product of 200,000 years of human evolution, is calibrated to the microbial communities of the modern world. It would not be calibrated to the microbes of the Cambrian or the Devonian or the Cretaceous. Even if you survived the chemistry and the predators, you would face infections from organisms your body has never encountered. In some prehistoric oceans, this would be the first thing to kill you, before any predator or chemical reached you. The sixth category is the food web. Even if you somehow survived everything else, you could not feed yourself in a prehistoric ocean. The species that exist in any given era are calibrated to that era's biochemistry. The fish you might catch and eat in the Cambrian would have proteins and fats that your digestive system could not properly process. The plankton you might filter from the Ordovician would contain trace toxins and unfamiliar compounds. Long-term survival in a prehistoric ocean would require not just surviving the immediate threats but eating, and the food itself would not be food in the way your body understands it. 6 categories: atmosphere, water chemistry, temperature, predators, microbes, food. 6 different ways the modern ocean has had to come together to be habitable to us. 6 different categories of contingency that had to align before our species could exist as marine-tolerant creatures. There is a story that gets told. It goes something like this. Humans are the pinnacle of evolution. We are intelligent and adaptable and capable of surviving in any environment we choose. We have built cultures in Arctic ice and tropical rainforests and arid deserts. We have crossed oceans and climbed mountains and walked on the moon. We are, by any reasonable measure, the most successful species on the planet, and our success comes from our flexibility, our intelligence, our ability to adapt to whatever conditions we encounter. This story is almost entirely wrong. We are not flexible. We are not adaptable. We are extraordinarily narrow in our environmental tolerances, more so than almost any other species on Earth. The reason we have spread to so many different climates is that we use technology, clothing, shelter, fire, tools to create artificial pockets of livable conditions inside hostile environments. We do not actually survive in Arctic ice. We survive in heated buildings inside Arctic ice. We do not actually survive in deserts. We survive with water bottles and shade and the metabolic luxury of agriculture in deserts. Without those technologies, we are limited to a very narrow range of natural conditions. And those conditions are the conditions of the modern world. Think about what this means for our evolutionary heritage. The lineage that produced us has been around for a long time, but the version of us that evolved to fit the modern world, anatomically modern Homo sapiens, has been around for only about 200,000 years. That is the time window in which our specific physiology was tuned to specific environmental conditions. Those conditions are the conditions of the late Pleistocene and Holocene. Modern oxygen levels, modern temperatures, modern pH, modern microbial communities. We are calibrated to one moment in the planet's history, and that moment happens to be now. Our core body temperature must remain within about 2 degrees of 37 degrees Celsius. Our blood pH must remain within a narrow range around 7.4. Our blood oxygen saturation must stay above about 90%. Our salt and water balance must be maintained within tight limits. We need oxygen in the atmosphere at about 21%. We need temperatures within a relatively narrow band. We need protection from a long list of potential pathogens that our immune systems have specifically evolved to recognize. None of these tolerances are particularly broad. None of them would extend to most prehistoric ocean conditions. We are calibrated to one specific configuration of marine and atmospheric chemistry, and that configuration is the configuration of the modern world. The fish that share the modern ocean with us have similar narrow tolerances. The dolphins, the whales, the sharks, the corals, the plankton, all of them are calibrated to roughly the same modern conditions. We are part of an extended community of organisms that all evolved together to fit the same window of marine and atmospheric chemistry. We share an evolutionary moment with them. The tropical reef fish you see on a snorkeling trip evolved in essentially the same conditions you are comfortable swimming in. But here is the deeper question. Why is the modern ocean configured the way it is? Why did it become habitable to creatures like us? The answer is, in some sense, that it did not become habitable for us. We became habitable for it. Our entire lineage, going back through primates, through mammals, through reptiles, through amphibians, through fish, evolved within the conditions of the late Cenozoic ocean and atmosphere. Our biochemistry was tuned generation by generation to match the chemical environment of this period. The modern ocean did not happen to suit us. We happened to evolve to suit the modern ocean. This means that for almost all of Earth's history, no animal resembling us existed. The lineage that produced us was, for billions of years, completely different from us single-celled organisms in the Archean, simple multicellular animals in the late Proterozoic, fish in the Devonian, amphibians in the Carboniferous, primitive mammals in the Mesozoic. Each of those ancestral forms was adapted to its own ocean, its own atmosphere, its own chemistry. And each of those ancestral forms would have died if you placed it in a different era's ocean. The Devonian fish would have died in the Hadean. The Cambrian arthropod would have died in the Permian. Every form is locked to its time. We are no exception. We are locked to our time. The window of livability we occupy is brief. It opened in the late Pleistocene, perhaps 200,000 years ago, when our species first appeared. It is open now. It will not stay open forever. Let us think about that for a moment. Because the closing of the window is, in some sense, more interesting than the opening. The modern ocean is, in geological terms, in the middle of an ice age, the Pleistocene-Holocene glacial cycle, which has been ongoing for the last 2.5 million years. Glacial periods alternate with interglacial periods, and we are currently in an interglacial. In 10 or 20,000 years, under normal Pleistocene rhythms, the cycle should swing back toward glaciation. Sea levels would drop. Tropical zones would contract. The marine ecosystems that we know would shift toward the equator. The ocean would still be inhabitable to humans, but it would be a different ocean. Beyond that, on longer timescales, the ocean will continue to change. The continents will continue to drift. The atmosphere will continue to evolve. The microbial communities will continue to shift. The species that occupy the modern niches will be replaced by other species. In a few million years, the ocean will look noticeably different. In tens of millions, it will look very different. In hundreds of millions, it will be unrecognizable. And at some point, well before the sun engulfs the Earth in its red giant phase, the ocean will become uninhabitable to organisms like us. The exact mechanism is uncertain. Perhaps the planet will warm too much. Perhaps the chemistry will shift in some way that makes seawater toxic to our kind of biochemistry. Perhaps oxygen will be drawn down again by some process we cannot predict. The mechanism does not matter much. What matters is that the window will close. The only ocean we can swim in will eventually become the only ocean we cannot swim in. This is what the prehistoric oceans teach us. Not that they were dangerous. They were dangerous, and we have cataloged the dangers. But more deeply, they teach us that the ocean is not a stable, eternal feature of the Earth. The ocean is a configuration, a specific arrangement of chemistry and biology and physics. The arrangement we have now is recent and temporary. The arrangements we have had before were different. The arrangements we will have in the future will be different again. We are guests in this ocean. Brief guests. We did not earn our place in it through any merit of our own. We simply evolved at the right moment to fit the configuration that happened to exist. We are no more entitled to our compatibility with the ocean than a Devonian fish was entitled to its compatibility with the Devonian Ocean. Both are accidents of timing. Now imagine the diver one more time. The same diver who has died in every prehistoric ocean we have visited tonight. Hadean, Archean, Proterozoic, Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, Miocene. In every era a different death. Boiling, suffocation, hydrogen sulfide, Anomalocaris, Camarasaurus, Pterygotus, Dunkleistus, Helicoprion. The chemistry of the dying Permian. The dead ocean of the early Triassic. Pliosaurus, Mosasaurus, Megalodon and Livyatan together. 13 deaths. 13 prehistoric oceans, each one finding its own specific way to refuse this particular kind of life. And then the diver returns to the present. The modern ocean. The 14th attempt. They step into the water. The water is the right temperature. The salinity is correct. The pH is correct. The dissolved oxygen content is correct. The dissolved gas mixture is correct. The microbial community is one their immune system can handle. The pathogens, if there are any, are familiar to their genome's defensive systems. The food web is compatible with their metabolism. There are predators in this ocean, but the predators are mostly avoidable, and the ones that are not avoidable are present at relatively low densities and relatively small sizes compared to the apex predators of any prehistoric era. The diver swims. They breathe. They look around. A small fish darts past. A patch of seaweed waves in the current. A turtle paddles past in the distance, moving slowly toward a nesting beach. Everything works. The water tolerates them. The atmosphere tolerates them. The ecosystem tolerates them. They are, for this moment, fully compatible with their environment in a way that they have not been at any other point in the imaginary journey we have just taken. This is the modern ocean. This is the only ocean in the entire history of the Earth that has had room for a creature like you. Out of 4.5 billion years of marine history, perhaps 200,000 have produced ocean conditions you can occupy. That is a window of approximately 1 part in 20,000. Less than the width of a fingernail on a meter stick. You are inside that fingernail right now, as you sit or lie wherever you are, listening to this. The ocean outside, wherever it is in relation to you, is the only ocean in deep time that would have you. You can step into it tomorrow morning if you choose. You can put on a wetsuit if the water is cold. You can swim. You can dive. You can spend hours in it and your body will keep functioning. The water will not boil you. The atmosphere will not suffocate you. The hydrogen sulfide that filled the deep waters of the Proterozoic will not poison you. The Anomalocaris of the Cambrian will not investigate you. The Dunkleistus of the Devonian will not slice you in half. The Pliosaur of the Jurassic will not crush you. The Mosasaur of the Cretaceous will not swallow you. The Megalodon and Livyatan of the Miocene will not take alternating bites of you. None of those things exist anymore. The oceans they ruled are gone. The chemistry they swam in is gone. The era of marine conditions they thrived in has been replaced by a new era of marine conditions. The era we are in, the era that suits us, the brief window that has opened just long enough for our species to evolve and exist within it. There is something almost embarrassing about how lucky this is. We did not earn it. We did not work for it. The ocean simply happened to be configured the right way at the moment our species evolved, and so we exist and we can swim and we can fish and we can build coastal cities and shipping industries and recreational beach economies on the back of an environmental coincidence that did not occur for the first 3.9 billion years of the planet's history and will not last forever. The geological perspective is sobering. The window of marine habitability for our species is small. It is bounded on both sides by oceans we could not survive in. On the early side, all the prehistoric oceans we have visited tonight. On the future side, whatever oceans the planet will have when our window finally closes. We exist in a sliver, a thin slice, a geologically transient moment. But within that moment, there is the ocean. There is the modern ocean. Our ocean. The only one that has ever been ours. There is something to sit with there. As you drift toward sleep, hold the image of the ocean in your mind. Not the prehistoric oceans we have just visited and died in. The modern one. The familiar one. The one whose surface ripples in the way you know, whose color is the color you expect, whose smell is the smell of sea salt and seaweed that has been the smell of sea salt and seaweed for the last few 100,000 years and not for one moment before that. The waves are rolling onto shores where humans walk barefoot in warm water that does not kill them. Children are learning to swim in shallow water that is the right temperature, the right salinity, the right chemistry, the right everything for human existence. Fishermen are pulling in nets full of fish that human bodies can digest. Surfers are riding waves whose physics happens to be exactly the physics human balance evolved to handle. Divers are exploring coral reefs that contain pathogens human immune systems can recognize and counter. Sailors are crossing oceans whose temperatures and currents are predictable enough for humans to navigate. Every one of these activities is contingent on the modern ocean being configured the way it is. Every one of these activities would have been impossible, instantly, irreversibly impossible, in any prehistoric ocean. The modern ocean is a gift, a temporary, contingent, easily overlooked gift. It is the gift of being able to exist in water at all. The gift of having a place to swim. The gift of being part of a marine world that does not actively reject your kind of life. We do not usually notice the gift. We assume the ocean is just the ocean. We assume it has always been the way it is and always will be. We assume that if we could go back to any era of the past, we could swim in those waters too. The reality, as you now know, is the opposite. We can swim in the ocean we have. We could not swim in any of the oceans the planet has had before us. We probably will not be able to swim in the oceans the planet will have after us. This is our window. This is our slice. This is our specific, narrow, beautiful arrangement of marine conditions, and we are inside it now, and we are inside it tomorrow, and we will be inside it for as long as our species lasts. That is, when you really think about it, more than enough. That is, in fact, a kind of miracle. The miracle does not need to last forever to be a miracle. It only needs to last long enough for us to notice it. Tonight we have noticed. The Hadean Ocean, with its boiling acid water, is gone. The Archean, with its methane sky and oxygen-free atmosphere, is gone. The Canfield Ocean of the Middle Proterozoic, with its sulfide-laden depths, is gone. The Cambrian, with its anomalocaris and trilobites, is gone. The Ordovician, with its Camarasaurus nautiloids, is gone. The Silurian sea scorpions are gone. The Devonian Dunkleistus is gone. The Carboniferous Helicoprion is gone. The End-Permian Dead Ocean is gone. The Jurassic pliosaurs are gone. The Cretaceous mosasaurs are gone. The Miocene megalodon and Livyatan are gone. Every ocean that ever would have killed you is gone. Every single one. Replaced by the one we have now. The one that has you. The one that is your brief and unusual home. Let me leave you with one last thought before you sleep. Earlier in this documentary, I described you stepping into the warm Devonian water and seeing what you thought was a Caribbean reef. The corals were stromatoporoids. The fish were placoderms. The turtle was not a turtle. The Dunkleistus came around the bend and killed you in 2 minutes. Now imagine the same scene but reversed. Imagine that a Devonian fish, a small one, maybe an early lobe-finned creature, a remote ancestor of all modern vertebrates, was somehow transported forward in time to the modern ocean. It is dropped into the warm water of a Caribbean reef. The water looks similar to its home water. The temperature is similar. There are reefs, although the reefs are made of different organisms now. There are fish, although the fish look strange. Within minutes, the Devonian fish would die. The chemistry is wrong. The oxygen content is too high. The microbial environment is full of pathogens it has no defense against. The predators are organized differently than in its home seas. The salinity is slightly different. The trace metal composition is different. The dissolved organic matter is different. Modern seawater is, to a Devonian fish, a foreign environment, and the Devonian fish cannot survive in it. Each era's life is locked to each era's ocean. The Devonian fish cannot visit our ocean any more than we can visit theirs. Both directions are closed. Time is one way. The lock works in both directions. This is true of every species in every era. The Cambrian anomalocaris could not survive in the modern ocean. The Jurassic pliosaur could not survive in the modern ocean. The Miocene megalodon could not survive in the modern ocean. Each of them, transported forward in time, would die for the same reason you would die transported backward. The chemistry is wrong, the chemistry is not theirs. Each ocean fits its time. Each fits the creatures evolved to live in it. Each is hostile to creatures from other times. This is not a defect of any particular ocean. It is simply how biological environmental coupling works. Organisms evolve to fit their environments. Environments shape the organisms that evolve. When we look back at the prehistoric oceans and ask whether we could survive there, the answer is no. But the question is, in some sense, unfair. We were not built for those oceans. The creatures who lived there were. They thrived. They lived their lives. They did exactly what we are doing now in our ocean in our time. The arrangement of biology and environment that produced their flourishing was their arrangement, and it worked perfectly for them until it changed. We are in our arrangement. Our flourishing is happening now. Our biology and our environment are working perfectly for us in the brief window that the modern ocean provides. Here is a strange thought to sit with as we approach the end of tonight's journey. If you can hear these words, if you can understand them, if you can imagine the prehistoric oceans we have visited tonight, the boiling Hadean, the methane-skied Archean, the sulfide-poisoned Proterozoic, the strange and lethal Cambrian, all the way through to the megalodon-haunted Miocene. If you can imagine any of that, then you exist in the modern ocean's window. You are inside the small slice of time that has produced creatures capable of imagining their own absence from other times. That is the paradox. The only kind of mind capable of asking whether prehistoric oceans were habitable is the kind of mind that could only have evolved in the ocean we have now. The Devonian fish did not wonder about other oceans. The Cambrian Anomalocaris did not wonder about other oceans. The Permian creatures dying in the heat and the hydrogen sulfide did not wonder, in their final moments, whether some future ocean might be more hospitable. The wondering belongs to us, and we belong to this moment, and this moment is the only moment in which the wondering can occur. This means something interesting about the question we have been asking all night. The question, could you survive in a prehistoric ocean, is, in some sense, a question that can only be asked from one side. If you had been an inhabitant of any prehistoric ocean, you would not have asked it because you would have been a different kind of creature with a different kind of mind, busy with the business of living in your specific ocean, not contemplating ones that did not yet exist or had ceased to exist. The question is a privilege of the present. The question requires a present in which to be asked. And the present is contingent. It exists because the chemistry happened to align, the temperatures happened to stabilize, the right microbial communities happened to be in place, the right oxygen levels happened to accumulate, all of it, the entire suite of conditions that allows you to be here listening to this, came together not because they had to, not because evolution was aiming at producing creatures like you, but because that is how the chemistry of this particular planet happened to play out across 4.5 billion years of slow molecular accumulation and shifting conditions. You are accidental. The modern ocean is accidental. The compatibility between you and your ocean is accidental. The fact that you can swim, that you can breathe, that the waters of the planet you happen to live on are not at this moment trying to kill you. All of that is the result of contingencies stacked on contingencies, none of which had to occur, all of which could have gone otherwise. And yet they did occur. They did go this way, not the other ways. And so here you are, in your body, in your moment, in your ocean. Maybe there is something to be said for that. For the simple fact of it. Not for the meaning of it, because there is no inherent meaning, just as there was no meaning to the prehistoric oceans, no purpose to the Hadean's boiling water or the Permian's dying fish. The deep history of the planet did not have a point. It was simply what happened. And what is happening now is also simply what is happening. The waves keep rolling. The water keeps moving. The ocean continues to do whatever the ocean does, indifferent to whether anyone is around to swim in it. But you are around. You are around tonight. And tomorrow, if you choose, you can be around in the ocean itself, putting your body into the water that has been waiting for the right kind of body to emerge, and finding that, by the strange grace of geological coincidence, your body is the right kind. The water will receive you. It will not boil you. It will not poison you. It will not be patrolled by Anomalocaris or Dunkleistus or Pliosaurus. It will be simply the modern ocean doing what the modern ocean does, hosting the modern marine world, of which you are a brief and unlikely member. That is the gift of being alive now rather than then. Sleep well. The modern ocean is doing what it has done for the last few 100,000 years, providing a habitable environment for the species that evolved to fit it. The waves are continuing. The water is continuing. Somewhere, someone is floating on their back in warm seawater, watching stars come out overhead, perfectly compatible with their environment for that moment, alive in a way that almost no other moment in the deep history of the Earth would have permitted. That someone could be you tomorrow. Or it could simply be the knowledge that someone somewhere is doing exactly that in your ocean, the only ocean that has ever had room for your kind of life. The ocean that is doing exactly what it does, with no awareness of how briefly it has been doing it, or how briefly it will continue. Hold the modern ocean in your imagination. The warm water, the right temperature, the right chemistry, the right air above it. The fish that share it with you evolved alongside you, calibrated to the same conditions you are calibrated to. The whales whose distant ancestors were land-dwelling mammals 50 million years ago, returning to the sea after a lineage of one of those calibrating events. The corals descended from Cretaceous corals that survived the asteroid that killed the dinosaurs. The plankton communities that have been blooming and dying and blooming again in the same general way for tens of millions of years. All of it. The entire modern marine world. Yours. For now. While the window is open. The Hadean is gone. The Archean is gone. The Canfield Ocean is gone. The trilobite seas are gone. The Anomalocaris and the Camarasaurs and the Pterygotus and the Dunkleistus and the Helicoprion are gone. The N-Permian poison is gone. The pliosaurs and the mosasaurs are gone. The megalodon and the livyatan are gone. Everything that would have killed you in every prehistoric ocean is gone, vanished into the rocks of deep time, preserved only as fossils and chemical signatures and reconstructed scenes in documentaries like this one. What remains is the modern ocean. What remains is you, alive in it, compatible with it, one of the brief population of organisms in the long history of this planet that the present ocean has chosen to accommodate. That is, for tonight, enough. Be grateful. The ocean we have is the only ocean we have. The only one that has ever been ours. The only one that will ever be ours. It is enough. It is more than enough. The Cambrian seas are sleeping in their rocks. The Jurassic reptiles are sleeping in their fossils. The Devonian Dunkleistus is sleeping in its place at the bottom of the sediment column, layers of younger rock above it like a long blanket. Every prehistoric ocean is sleeping in its way, while the modern ocean continues, while the waves keep rolling, while the night turns slowly toward another morning of the brief window in which you and your kind happen to exist. Sleep well. You are alive in the only ocean that ever had room for you. The waves continue. The water continues. The ocean we know continues. That is everything. And it is enough. Sleep well.